Hi everyone, this is section 3.4, the real zeros of polynomials, and in this section we are going to attempt to find the real zeros of polynomials, so all of them. And to do that, there's going to be a few things I want to make note of. First of all, just some, what's the word I'm looking for? Some theorems, some identities, some truths, some random information first in this first video. I will do some examples in the second video, as the examples are going to take a little bit of time. And to be honest, this section and the next section a lot of times are kind of like we cross our fingers that we get lucky, if that makes sense. So first of all, I want to remind us here is that every polynomial, and this, to be honest, really doesn't make a whole lot of sense, but I'm going to put it in here anyway. And we know what a polynomial looks like. So I'll remind us that wonderful notation we used. That was our polynomial. And we did have n being bigger than or equal to 1. We do want it to be at least a linear polynomial, not a constant polynomial. And of course, we're going to keep that a sub n not equal to 0. Otherwise, we could have just rewritten it. If we have a polynomial, and we will extend this with complex coefficients. So we could have really, really ugly coefficients. However, we in this class will not. Has at least one complex zero. Okay? So we can say that it has one. Doesn't tell us how we can find it. Another piece of information. If p of x is a polynomial of degree n, so I'm going to be working with the one that's above, and n is bigger than 1, so at least a linear function, then there exists complex numbers, and we will use the letter C, so C1, C2, C3, all the way up to Cn, and yes, this n does agree with this n. So a third degree polynomial will have 3 possible complex numbers. They may not all be different. So we may have the 3 identical complex numbers, but we can rewrite this function in the form, so pull that a sub n out, or that a out, and this a is going to be that a sub n. Maybe I'll just write that a sub n in there. And we could write it as x minus c1, x minus c2, and so forth. In other words, we can factor it into linear pieces. Now, it does not say that these are all different. Okay, some more information. Every polynomial of degree n greater than or equal to 1 has exactly n zeros. So in other words, we can do this factoring n different times. We also would say that provided that a 0 of multiplicity k is counted k times. In other words, what this says, if we have x minus 2, x minus 2, x minus 2, so we'd have that x minus 2 cubed, we would count that 2, being the 0, 2, 3 times. So it would be said that 2 is a 0 of multiplicity, I'll abbreviate multiplicity 3. Okay, so I'm kind of getting a little bit of ahead of the ball game here. These things are kind of in section 5, but they will help us as well in section 4. I like to kind of do a little bit of 5 into 4 because there is such an overlap between section 3 and section 4 and section 5. So these little pieces actually do come from section 5. So I'll kind of pull out my book here and you can see them. So here's my book, okay, and I'm in actually section 5. So here's that fundamental theorem of algebra that I wrote down, that it has 1, 0. It's the fundamental theorem of algebra, so that's pretty important. It has a 0. Doesn't tell us how we find it. We can factor it. That was the complete factorization theorem. Then we had the 0 theorem, so that is also there. Okay, so those are the theorems that I want to pull from section 5 to kind of help us a little bit when we're doing section 4. The ones I want to get from section 4 though, and I'm just going to pull them out of my book. I'm not going to write them all down again. I suppose I could have done that here as well. But section 4, the first one, and maybe I should write it because, I don't know, helps you. I'm going to zoom in a little bit if I can here. Zoom in. There we go. Is the rational zeros theorem. Okay, so now we've talked about how many zeros there are and so forth. If we have a polynomial, so again, polynomials look like this. That wonderful ax to the n minus 1 and so forth. If it has integer coefficients, so really nice numbers, 3s, 5s, -7, all those wonderful integers. Again, a sub n, the first one is not 0, and the last one is not 0. The reason we don't want the last one to be 0 is because if it was, and we're looking for zeros, we would first thing factor out an x, and we'd be down one more. So we kind of look at something that isn't easily already factorable by pulling out an x. So these rational zeros, so if we have a rational zero, it doesn't say we will have one. It just says if we have a rational zero, rational being some sort of fraction, whole number, integer, will look like a p over q. So rational means fraction. And p and q are integers, positives or negatives, where p is a factor of the constant term and q is a factor of the leading coefficient. This will come in handy when we're trying to find zeros. And that's what we're going to be doing in my second video when I actually go through and try to find them. So this gives me an idea of what those rational zeros will look like. The other piece of information that I'm going to pull out that's going to help me, and you'll see me use it in the next video, is Descartes' rule of signs. Okay, so first of all we have a polynomial, and this one we can have just real coefficients. And what we're going to do is we're going to look at the number of positive real zeros. Okay, so positive real zeros is equal to the number of sign changes, or less than that by an even whole number. And again, in the video when I'm going through examples, I will explain that. So if we want to talk about how many negative real zeros we have, what we're going to do is look at p of negative x and we're going to look at our sign changes, the variation in sign. How many times does it change signs? And will be that, it'll be equal to that or less by a whole number. And again, I will show you in examples in the next video. Right now I'm just giving you dumping out all the information. Okay? We will use it in a moment. The last one, and this one I never really use much, is this upper and lower bounds theorem. This one I use if I happen across it. If it shows up, great, then I can help myself. If I don't go looking for it, so to speak. But it is the upper and lower bounds theorem. So if we divide a polynomial by x minus b, so b is greater than 0, so 7, 5, 3, whatever, using a synthetic division, and that very last row that we get has no negatives, absolutely no negatives, then b is going to be an upper bound for our zeros. In other words, our polynomial is going to be going up from that point on. If you divide it by x minus a, where a is less than 0, so in other words, a positive, an x plus 7 or x plus 6 we're dividing by, and we get that it alternates, alternately non-positive and non-negative. So positive, negative, then kind of not looking at the zeros. Then a is a lower bound, so we won't have any smaller ones. Again, I don't use this one straightforward. I don't go looking for my upper and lower bounds. Most people do not, but they use this fact when they're looking for our zeros. Okay, now we have all this information. What in the world is it going to help us do? And that's where my next video will be, is when we're going to be finding those real zeros, at least attempting to find. So in the next video, I'm going to go through at least 1 or 2 examples where I can find my real zeros, going through using all these things that we've learned. So I'll see you in the next video.